It was a device that virtually nobody believed in. The Scanning Electron Microscope, or SEM, is famous for its amazing three-dimensional photographs. It is hard to imagine a world without such a machine, not only for eliciting the curiosities of children and nerds like me, but also for diagnosing semiconductor issues. Despite its usefulness, we wouldn't have the commercial SEM today as we know it without the quiet, persistent efforts of a single man. In this video, we cover the long and difficult birth of the Scanning Electron Microscope. Charles Oatley was born in 1904 to the owner of a bakery and a school teacher. His father did not have much in terms of an education, but passed on a love for science and technology. One of Charles's early toys was a microscope. Oatley grew up to be a formal and soft-spoken man, a consummate English gentleman. He graduated from Cambridge and worked in industry, building radios. This got him into radar development during World War II. After the war, Oatley was appointed a lecturer at the Cambridge University Engineering Department. His goal there was to help upscale the university's research effort in the new and bustling world of applied physics. He tried to find projects for his students to do, speculative projects that train them and exercise their creativity but can still be useful. In his view, such university projects can be different from those in industry. PhD students cost less. The stakes of failure are far lower because the student is judged on the excellence of their work rather than the end result. So you can research more wild and woolly things knowing that the end goal isn't necessarily a commercial product. This search eventually took him to the electron microscope. In 1926, a German physicist named Hans Walter Hugo Busch showed that you can use magnetic and electric fields to guide the electrons of an electron beam in a certain direction. These principles enabled the possibility of a lens that can act on beams of electrons like how optical lenses act on visible light. Electron wavelengths are almost 5 orders of magnitude smaller than that of optical light. In theory, an electron-based microscope could produce resolutions far superior to that of optical microscopes. Inspired by Busch's discovery, a team of 2 men in Berlin set out to build such a machine. In 1931, Max Knoll and Ernst Ruska built the first conventional transmission electron microscope. The word transmission is in the name because the machine sends a beam of electrons through an ultra-thin slice of the specimen. After that, we focus the beam and turn it into an image. Unfortunately, at the time, it was difficult to slice the specimens thin enough in order to get a good image. This lasted until 1940, when Hans Moll introduced replicas, a method of using plastic and metals to prepare a specimen for TEM imaging. Knoll and Ruska knew that a second type of electron microscope was possible, one that would work more like a traditional optical microscope. After his work on the transmission electron microscope, Knoll joined the Telefunken company to build TV camera tubes. In 1935, he built an electron device based on this second idea in order to study a component of his tubes. He put the sample into one end of a glass tube with an electron gun on the other side. The electron beam is scanned across the sample, and electrons reflected back or emitted from the sample are collected, amplified, and then used to create a magnified image of the sample surface. Knoll called his device Der Elektronenabtaster, which means electron scanner in German. Sounds cooler in German if you ask me. Knoll's machine could magnify about 10 times, but not much more due to the width of its electron beam probe. Interestingly, he did not use electron optics to try shrinking that width. He certainly must have considered it. Maybe he passed because the current setup already met his needs and sufficiently sensitive electron detectors were not available. Ruska later won the Nobel Prize for Physics in 1986 for his work in electron optics. I reckon Knoll would have won part of that Nobel as well had he not passed away in 1969. Meet the German scientist Manfred Baron von Ardenne. He was born into a wealthy family, which let him run his own lab. Brilliant and self-taught, he received his first patent at the age of 15. In 1931, he demonstrated the first fully electronic television system. It used cathode ray tubes to produce images, which is pretty cool. In 1936, Siemens contracted Ardenne to design and build a new electron microscope to avoid an issue in existing TEMs. In an electron stream, not all electrons are made equal. Some have more energies than others, causing them to react differently as they accelerate and pass through the lens, creating aberrations in the image. So Ardenne built a microscope that scanned an electron beam across the sample line by line. Today we call this a scanning transmission electron microscope. Scanning because of how the machine scans across line by line, transmission because the electron beam still goes through the sample. Ardenne only spent 2 years on this. His machine was sophisticated but also limited. The beam was not powerful enough, and Ardenne did not have sufficiently sensitive electron sensors, resorting to photographic film. So it took 20 minutes to record an image, and since you can't see if the image needed focusing until after developing the film, you had to sort of wing that part. No images were ever published. A brilliant and creative mind, Ardenne probably would have been able to build something had there been time. He had all the essential principles down, including a correct theoretical model of the sample's interaction with the beam. When an electron beam hits the sample, 2 things happen. First, primary electrons from the beam are backscattered, as in they bounce back off the surface like ping pong balls. And then there is the secondary reaction. This is where atoms in the sample get energized by the primary beam and start emitting electrons of their own. Ardenne knew this, and so he was on the right path. But then World War II broke out, and Ardenne abandoned the project to work on a cyclotron for the German atomic bomb project. His electron microscope was destroyed during an air raid in Berlin in 1944. Later, Oatley calls him the quote-unquote true father of the scanning microscope. The ideas were right, but the times failed him. After the war, Ardenne worked for the Soviet atomic bomb program. Then he settled in East Germany and founded a research institute. He passed away in 1997 at the age of 90 with 600 patents to his name. A life of discovery and invention well lived. There is one last scanning electron microscope project that we should mention. The American radio company RCA did work on a scanning electron microscope of their own for a few years. The project was initiated and led by the famed inventor of the television camera tube, Vladimir Zworykin. The project started as something to build a new type of microscope, but then in 1940 the aforementioned Hans Moll introduced his replica method. Now suddenly the transmission electron microscope had become a formidable competitor, and the RCA team had to adjust their system to accommodate. They focused on building a machine that can work on samples that we can't cut into thin pieces. In it, a tube generates an electron beam that hits the sample. Electrons then reflect off or are emitted by the sample. Those electrons are accelerated back up through another set of electron lenses and an electron multiplier tube to intensify the image before hitting a detector screen for imaging. This SEM did not image smaller features than existing TEMs. At the same time, the downsides were substantial. It was expensive. It took 10 minutes to make an image, and noise often clouded the images. RCA rightly decided to move on and focus on their transmission electron microscope products. There was little more work done on scanning electron microscopes for several years when Charles Oatley came along. Oatley first came onto the scanning microscope idea through a pre-existing interest in electron optics. Soon after he started, he asked one of his PhD students, K.F. Sander, to try building a TEM for their project. Sander started on it before abandoning it for something else. Sander's work was not revived because soon after that, Oatley's colleague Vernon Cosslett began some work in TEMs, and the gentlemanly Oatley did not want to step on his colleague's toes. But Oatley did feel that a scanning electron microscope might be a good alternative. The previous body of work done at RCA had shown that its scientific principles were fundamentally sound. There also seemed a pathway towards solving the RCA SEM's long recording time and noise issues. The two problems were related. The longer it took to record the image, the more noise there was. Oatley reasoned that if they can somehow collect more of the electrons coming back from the sample, then you can both cut the recording time and improve the noise. You might even be able to put the imaged result on a cathode ray tube screen for more convenience. And how can you collect more electrons? Well, if you recall from the original RCA SEM, electrons from the sample are run through lenses and accelerators before hitting the multiplier and then the detector. We lose some of them by doing this. So what if we just send them right into the multiplier instead? There are also possible improvements using technologies developed during the war, most notably an electron multiplier that Oatley felt might be better than RCA's. It was built by his colleague at Cavendish Laboratory, A.S. Baxter. This was all a hunch, and no clear-thinking manager at a company would authorize an R&D project on such thinking. But like as I said, a PhD project was different. The stakes were lower. So Oatley assigned Dennis McMullen, a student uniquely suited for the task, with analog, tube, and radar experience from during the war. The project received a small grant and had a bunch of valves, tubes, and other components at their disposal. People had low expectations. If RCA and its brilliant minds failed to get this to work, how can a random Cambridge student with £1,000 and some tubes do better? But over the time he spent on this project from 1948 to 1959, McMullen produced a working proof of concept machine. He took over the uncompleted TEM left behind by Sander and added a power supply, electron lens, and cathode ray display unit he built with his own hands. This machine had a more powerful electron probe, as well as a tilt. In an attempt to get better contrast on the SEM's images, McMullen tried tilting the sample at a far higher angle relative to the beam than before tried, 25 to 30 degrees as compared to the previous 2 degrees. What you got were the beautiful three-dimensional images that scanning electron microscopes are so famous for. The tilt also helped get more electrons into the electron multiplier, enough to put some images on a cathode ray tube display for a few seconds. The results were promising enough that Oatley continued the project after McMullen left the lab in 1953, handing it over to Ken Smith. Ken Smith contributed several improvements to the machine, the most important of which was to collect the low-energy electrons emitted from the sample as part of secondary reactions. As I mentioned, Ardenne had pointed this out before, but when McMullen was building his machine, he did not collect those secondary electrons because he thought they would hurt the image quality. As it turns out, collecting those secondary electrons, as well as emitted light and X-rays from the sample, boosted image quality by a factor of 50. Oatley's subsequent graduate students like O.C. Wells, Gary Stewart, and Thomas Everhart locked down the design and improved components for collecting backscattered and secondary electrons. By 1960, Oatley and his team had largely completed the machine. Oatley oversaw their efforts, checking in frequently with questions, discussion, and suggestions to move the research forward. Together, they developed techniques for using the device. Some of the science made with the device was published in scientific journals, though not all of them. Some academics from Canada's Pulp and Paper Research Institute saw the device in action and asked for their own. It wasn't being sold commercially, so the Cambridge team custom built one and shipped it to Canada. Since 1955, Oatley had tried to convince a company to produce the device for customers, but at the start, people questioned its commercial viability. The scanning electron microscope offered far less resolution than its sibling, the transmission electron microscope, hundreds of angstroms rather than the latter's 10 or 20 angstroms. On the other hand, the SEM did not require the long and tedious preparation of replicas. This not only made it more convenient to use, but also suited items like fibers, often susceptible to burning whilst being prepared. Furthermore, SEM images have that fantastic and distinctive depth of field. Can't dispute that these SEM images just look amazing. Nevertheless, experts initially assessed the world market for the SEM device at just 15 units. This disinterest lasted until Oatley approached the managing director of the Cambridge Instrument Company with his idea. The Cambridge Instrument Company itself has a fascinating history. The company was founded in 1881 as a partnership between a wealthy student, Albert George Dew Smith, and Horace Darwin, the youngest surviving son of Charles Darwin. Yes, that Charles Darwin, the guy forever remembered for collecting the first fossils of a 9-foot-long capybara, and some stuff about evolution or whatever. Anyway, Horace Darwin was a competent mechanical engineer, and the company he co-founded produced equipment for physiological labs. For example, a breathing mechanism that pumped chloroform into an animal while it was being operated on. Later, Darwin took sole control over the instruments part of the business and continued producing instruments like thermometers, galvanometers, and thermographs over the years. It became publicly traded and continued on doing what it was doing. By the late 1950s, the company had gotten to be in need of a little fresh blood, so they hired Harold Pritchard, an Oxford mathematician, to reboot R&D and get some new products out there. When meeting Oatley, Pritchard had actually been interested in a different product. That was the Microscan, which today we call the Electron microprobe. It fires an electron beam at a sample in such a way that causes them to emit X-rays, which the instrument reads. The Microscan sold well. It did something no other instrument can do, and that finally convinced Cambridge to take a chance on Oatley's scanning microscope idea. In 1962, DuPont's Canada team saw a prototype of what was called the Stereoscan, SEM, at the Institute of Physics and Physical Society exhibition, and having used the SEM previously built for the Canadian Pulp and Paper Institute, they put in a solid order for the first production machine. The SEM had many parts in common with the electron microprobe, so in theory it should have been relatively easy. But an issue came up that when someone tried to observe at a resolution of about 50 nanometers, extremely small vibrations ruined the image. This first machine was delayed for literally years in order to deal with this problem, which annoyed DuPont. Finally, Cambridge shipped its development machine over to them, dropping it down from a forklift onto a concrete sidewalk in New York. To help get the program off and running, the UK government then chipped in. They offered to fund the purchase of Cambridge's first few machines by British universities. So in 1965, Cambridge managed to build 5 commercial machines, which sold well. That was the turning point. A publicity campaign hauled in orders for 20 more machines, and that was that. By 1971, 520 Stereoscans had been shipped to customers. We have a hit. The scanning electron microscope has influenced virtually every part of the science and technology worlds, but the semiconductor industry has especially benefited from its bounty of gifts. The fact that you did not have to prepare replicas for samples made it far more convenient than the transmission electron microscope. Oatley realized this early on and assigned one of his students, Gary Stewart, to add an ion beam to the SEM for additional measurements. Though filters had to be added to remove oxygen ions from the beam, they were causing oxides to form on the surface of the etched chips. This convenience, as well as the microscope's high contrast images, made it easy for technicians to look at malfunctioning chips to see if they might have a broken connection, an invasive particle on it, or some other flaw. As integrated circuits have gotten denser over the years, this has pushed the SEM industry to keep up. This includes the use of digitization and software to improve imagery and shrinking the resolution. I want to thank an anonymous friend of the channel who works at Carl Zeiss for suggesting this topic. Unfortunately, Cambridge's historic role in the development of the SEM did not save it financially. Persistently high R&D and manufacturing costs, as well as a few bad acquisitions, later cost Pritchard his job. As it turned out, SEM-like devices had been invented intermittently in Japan, France, and the Soviet Union. The British firm Metropolitan Vickers/Associated Electrical Industries even sold one SEM-ish unit back in 1959, but it failed to work well. But when Cambridge demonstrated the instrument's commercial viability, others rushed in. Fierce competition ensued, particularly from the Japanese. The first Japanese SEM came just 6 months after the Stereoscan's debut. In 1968, Cambridge faced a hostile takeover from another firm, forcing them to sell themselves to George Kent Limited, another British instruments maker. A few years later, in 1974, George Kent was itself acquired by the Swiss electronics company Braun Boveri. In doing so, Cambridge was spun off once more as an independent company. Sometime after that, Cambridge becomes part of the famed German company Carl Zeiss. Charles Oatley retired from Cambridge in 1971, but continued to spend his retired life on the development of his microscope. 3 years later, he was knighted. In 1982, he published an iconic, highly cited paper on his work, humbly titled, as always, The Early History of the Scanning Electron Microscope. It was a critical source for this video, and I highly recommend it. Oatley spent the rest of his life tending to his garden, passing away at the age of 92. His students remember him as a quiet, humble man who paved the way for his students. And many of his students indeed went on to great things. For instance, Ian Ross was a transistor pioneer and went on to be the president of Bell Labs. Thomas Everhart became the 5th president of the California Institute of Technology. And Alec Broers is an e-beam pioneer and became Cambridge's vice chancellor, which delighted Oatley. Carl Zeiss Microscopy continues to honor the legacy of Oatley and his team at Cambridge Engineering, with various pages explaining his story. A quiet man who made a deep impact on his students, and through persistence, opened up an entire new world for all of us. What a legacy. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.